Hello, everyone, and welcome again to Neville, the best platform around for distance learning in business, finance, economics, and much, much more. My name is Saba, and today we're investigating one very important issue for risk management, namely how to model volatility and volatility scaling when our observations are not independent, when there is serial dependency, serial correlation, or autocorrelation. This video actually is a response to a comment left by Dingxin Cheng under one of our previous videos. So a hat tip to you, and I hope that you find this video helpful, as all of you will. Well, as you can remember, we have already investigated how to scale volatility when we assume that our observations in previous example and in this example as well, these would be market returns, are independent and identically distributed. We assumed that the stock returns were independent and normally distributed, but this volatility scaling formula can also be used when you assume the returns are non-normal and they come from any other theoretical distribution, provided that variance makes sense. Therefore, variance is defined for this distribution and it's not infinite. We'll talk about some distributions where variance is undefined or infinite in future videos on stock return modeling, but without getting too far ahead of ourselves, let's talk about what we can do when the independency assumption is violated. That's what sometimes happens on some of the less efficient stock markets, like emerging markets, or for some of the financial instruments that are not liquidly traded, or where a lot of irrational behavior is being manifested by market participants. Well, also, that is something that can happen on an irrational market in general when there is a lot of sentiment driving the trading activity. That's something we can observe even today, where there's a lot of panic on the stock market regarding the influence of the current pandemic, and so on and so forth. That can be applicable to a lot of various cases in finance and economics. Well, what it means when we say that returns or any other time series data is autocorrelated, it means that past observations of any variable that we observe affect current observations, or that current observations affect future observations. Well, how can we check for that, and how we can reformulate it in terms of stock returns? Well, in terms of stock returns, autocorrelation would imply generally overreaction or underreaction of the stock market to past information. For example, if we would see positive autocorrelation, so higher returns in the past leading to higher returns in the present, or, which is the same thing, higher returns today generating higher returns tomorrow, we could infer that there is prominent underreaction present on the market. When new information is released to market participants, they do not fully reflect it in asset prices when it's released. So some of this adjustment has to happen in the future. That's why positive autocorrelation can most of the time be referred to as market underreaction. On the contrary, if there is negative autocorrelation, so higher returns yesterday lead to lower returns today, or even negative returns today, that would imply overreaction. That is, that the market would overadjust to information releases, and therefore some of this movement will have to be compensated by a movement in the opposite direction as time passes. How to measure it? Well, to measure it, we can just use a simple correlation coefficient between stock market returns and stock market returns taken with a lag of 1 day. So we'll see how tightly are stock returns today and tomorrow associated. And the correlation coefficient would give us the idea on which direction this relationship is observed and how tight, how intense this relationship is. So as with any correlation coefficient, we'll get a number between -1 and 1. Well, the absolute value of the coefficient will tell us about the magnitude of the relationship. So a value around 0 in terms of absolute value would tell us that the relationship is very weak. A value close to 1 in terms of absolute value will tell us that the relationship is very strong and pronounced. And the sign will tell us whether the relationship is direct, so positive autocorrelation in our terms, or inverse, or in our case, it will be negative autocorrelation. So to measure it, we will just produce a time series of lagged returns. So here we'll have, again, the data on daily values for S&P 500 over the past 5 years. And here we'll already calculated the returns. So to generate lagged returns, we just have to refer to the value of the return yesterday for each of the days the data is available for. And that's how we'll generate lagged returns for each of our respective observations. And automatically click it all the way down and see that the return on the 2nd of January is the lagged return for the return on the 5th of January, and so on and so forth. Now, to figure out the autocorrelation coefficient, let's just use the correl function. That will give us the correlation coefficient for any two arrays of data. So here, we need our data arrays to be exactly of the same length. So we cannot use this observation as we do not have the lagged return for this observation ready as for now. So we'll start from here, press Shift Control down, and get the whole array, and then press here and press Shift Control up. And that's how we'll get both arrays. And now we can press Enter and figure out that the autocorrelation is minus 0.002, which would imply that the S&P 500 is very weakly but negatively autocorrelated. Generally, such a small value of the correlation coefficient would manifest that the market is not autocorrelated, that the observations are indeed independent, and that's one of the reasons why you could use the usual square root of n standard deviation scaling formula in case of S&P 500. But let's stick to the most accurate approach right now and figure out what would be the volatility scaling process if we believe that the returns are not independent, that they are autocorrelated. And let's try and scale our variance for a 5-day period. So if we would have assumed that the returns are independent, then we could just calculate a 1-day variance using a sample variance formula, so var.s, and have the initial array of returns here. And then, as we assume independency, we could apply the standard linear variance scaling. So we'll just need to multiply the 1-day variance, so daily variance, onto the length of our period. So variance would scale linearly, and the 5-day variance would be just 5 daily variances. So straightforward enough. So that's what would a variance in terms of 5-day periods assuming independency be. Now, if the observations are not independent, what can we do? Well, we can think back and understand what allowed us to use the linear scaling in the first place. Well, actually, it is just the formula for the variance of a sum, the variance of a sum of random variables that, given independency, allowed us to arrive at this conclusion. So this is a basic formula in mathematical statistics that basically says that the variance of the sum of two random variables equals to the sum of their variances. So variance of x plus y equals variance of x plus variance of y. But then there is an added term that can be interpreted in two different ways. We can either say that that means plus 2 covariances between x and y, or so that we don't have to calculate the covariance separately, we can also treat it as plus 2 times the product of the standard deviations of x and y times the correlation between x and y. We can already see that if we assume independency, and that allows us to assume that correlation between x and y is 0, then we're left just with this bit of the formula here. And if we had n variables instead of 2, we still could just sum them all up. And as we assume that they are identically distributed as well, so the variance of x equals variance of y and equals the variance of every single observation we are concerned with, then we could just multiply the variance by n, then say that the variance scales linearly, and then take the square root, and say that standard deviation or volatility scales as the square root. But if we are not assuming independency, if the returns or observations in general are autocorrelated, then we can't leave that bit out. If we have two variables only, then it's straightforward. It's just the correlation between the two, and then you multiply it by the product of their standard deviations. But if we have n variables, so multiple number of variables, if we want to scale beyond a 2-day period, and that's something you are concerned with most of the time, you want to scale to an annual period, you want to annualize, or at least go up to a monthly frequency, well, then you are not having just one additional component in this formula. You'll have to add pairwise all potential combinations of the product of every single possible combination of two variables and multiply it by the correlation between those two variables. This is already very tricky. Well, if you have two variables, you have just one added sum over here. If you have three variables, you'll have three. If you have four variables, that would explode to six. So basically, you'll have more and more different variables to estimate as your number of time periods you want to scale your variance to increases. So calculating them all separately is very difficult. So we make another assumption. That is, if we have autocorrelation between the returns today and yesterday, how can we use that to estimate the autocorrelation between the returns today and 2 days ago? Because in here, you can have generally any correlation coefficients between the returns, the observations that are separated by various lengths, the various numbers of days. Well, to simplify our calculations and to arrive at a very neat closed form solution, what we're assuming is that autocorrelation of order n, so it is the correlation between the returns today and the returns n days ago, is just the autocorrelation coefficient of order 1, so initial autocorrelation that we have calculated here, to the power of n. So it means that the returns 2 days ago are autocorrelated with the coefficient of r squared, the returns 3 days ago are cubed, and so on and so forth. And we can use this logic, the logic of this assumption that is most of the time relatively reasonable, to figure out the true 5-day volatility for our case with autocorrelation of minus 0.002. So now what we can do is we can use this logic to calculate this weight matrix. We will figure out the correlations basically of every single possible combination of facts, every single potential combination of variables. So basically what we need to do, first of all, we need to take the initial autocorrelation and we need to log that because, well, we assume that this is the only factor that influences autocorrelations of higher orders. And we need to raise it to the power of the difference between the lags. So if we are concerned with the correlation between variables of lag 1 and lag 3, for example, then we would not need to raise it to the power of -2, like 1 minus 3 or whatever. We would need to raise it to the power 2 because that's 3 minus 1. So what we need to do is we need to take the absolute value of the difference between those two lags. So the difference between that minus that. And here we lock the column and the row respectively. We can drag it around and it will recalculate the formula automatically. So we enforce the formula here and we get 1. That means that the correlation of the return at a particular day with itself is 1. Well, that's very intuitive because those are the same random variable. They should be correlated 4 to 1. And that's what corresponds to this added variances in the initial formula because, well, that is equal to the standard deviation of the variable times the standard deviation of itself, which gives you standard deviation squared or variance, times the correlation of it with itself. So 1, because the correlation of any variable with itself is 1. And that also gives you the idea of that the covariance of a variable with itself is actually just equal to its variance, which is another very um, well-known property in mathematical statistics. So now we can drag it to the right, we can drag it down, and see that the pattern is very regularized. So here we have the weightings that are equal to the first order autocorrelation coefficient if we are talking about lags of 1. And then we'll have the autocorrelation coefficient squared if we go to lags of 2 days, autocorrelation coefficient cubed if we go to lag of 3 days, and autocorrelation coefficient to the power of 4 if we go to the lag of 4 days. And that's all just mirrored alongside the diagonal that is filled with ones corresponding to the initial variances of those random variables. To see it more precisely, we can just change this autocorrelation coefficient arbitrarily to a larger number, because here, minus 0.02, already squared cubed is a very small number. So if we type 0.5, alternatively, we'll have a much clearer descent. So that is just 0.5, that's 0.5 squared, which is 1/4, that is 0.5 cubed, which is 1/8, and that's 0.5 to the 4th power, which is 1/16. But let's stick with our initial autocorrelation coefficient for now. And here, what we can say is that our scaling factor, in that case, would just be the sum of all those cells. So the diagonal would correspond to the n times we add together the variance of the initial random variable, so the variance of daily returns, and these coefficients below and above the diagonal would correspond to these covariances, or standard deviations times correlation coefficients. And the 2 over here, we can already see where it comes from. Well, it comes from the fact that the this table, this matrix, is symmetric. You have exactly the same autocorrelation coefficients if you consider a pair of leg 2, leg 1, or leg 1, leg 2. That's where the 2 comes in. So, to figure out the autocorrelation using this correlation structure, we just need to multiply this variance by the sum of all the elements in this matrix. And we'll see that in this case, the variance is slightly lower than the variance that we would have arrived at if we assumed independence, which is relatively straightforward to figure out because, well, if the autocorrelation is negative, it means that large movements to the stock return at 1 day lead to downward movements in the following day, and vice versa. If the stock prices decreased a lot today, they are more likely to rebound in the following day. So this, in terms of long-term volatility, acts like a stabilizer. If they were independent, the returns were independent, they could have fluctuated much further from the initial value, as there would be no negative autocorrelation process, no basically negative feedback loop that would bring them back closer to the initial value. And it's the reverse that happens when the autocorrelation is positive, as extreme movements tend to generate a positive feedback loop, generate more significant extreme movements in the following days, and that's why the variance for positively autocorrelated returns would be higher than the variance given independent. For example, if we just type in 0.5, as we already did a couple of minutes ago, we'll see that the variance would actually more than double as compared to the variance given independent. But returning back to our initial case, well, we already know how to precisely estimate variance scaling when the returns are not independent. But there's a lot of work. We have to construct a matrix, calculate the elements separately, and then figure out the sum of the elements of the matrix. Is there a formula that will allow us to do that for any value of the length of the period, any value of n, and any value of the autocorrelation coefficient? Well, it turns out there is. To do that, we should just generalize this logic and apply some relatively advanced mathematical formulas to figure out the closed form solution. So here is the general starting point in terms of the logic of variance scaling when returns are autocorrelated. So here we start with the scaling if that would be in place if the returns were independent, so just linear scaling. And then we add this term that basically adds all combinations of covariances between all potential pairs of lags of random variables. Well, here we move from lag 1 to lag n minus 1 because, well, the furthest to the past you can go is n minus 1 lags. So because you already go one lag into the past, and if you have n lags altogether, then the largest you can go is n minus 1. And then we need to figure out how many components are there, how many elements are there to sum up given a particular lag length. And here we see that there are 10 elements in the diagonal. So here it would be 5. And then as you go to the sides of the matrix, there are less and less elements when your lag length increases. And it increases exactly by 1 with every increase of the lag length. Here, if the lag length is 1, then you have 4 elements here and 4 elements here. So 2 times n minus I, which is the lag length. Then you go further back, you have 3 elements of lag 2, 3 elements of lag 2. That would be 2 times n minus 2, and so on and so forth. Here n was equal to 5, so this formula will give us 5 minus 2 equals 3 times 2 equals to 6. And we see that it's correct in that case because there are exactly 6 lags of 2 in our 5 n equals 5 scenario. And then we assume that they are identically distributed, so the standard deviations of all of them are exactly the same. So that would be just the sigma times sigma, so sigma squared, which would be exactly the same as here. And then we multiply by the correlation coefficient, the autocorrelation coefficient of a potential of a given lag order. And given our assumption, we just raise the initial correlation coefficient rho, that is the Greek letter for r. You can call the correlation coefficient rho, you can call it r, it doesn't matter. And we raise it to the power of I, so to the power of the lag order. That's exactly what we did here in the formula, where we raised the initial autocorrelation coefficient of order 1 to the power of the difference between the lags. Here we took the absolute value because we could have a negative difference between 1 and 3 and a positive difference between 3 and 1, for example. But here, as you have 2 over here, you have already accounted for both sides of the matrix. And we can see here that this formula, namely the second bit over here, is something that is called an arithmetic or geometric progression. An arithmetic progression is a series that changes with a constant step. So here, this is the bit. So you have n minus I. So for I equals to 1, it will be n minus 1. I equals to 2, it will be n minus 2, and so on and so forth. So that's something really easy to understand. And here we have a geometric progression. So rho to the power I. Geometric progression is the time series that has a common ratio. So every single So every following element of the series can be constructed by just multiplying the previous element by a fixed number called the progressions ratio. And here we can see that that's exactly what happens. You have row, row squared, row cubed, and so on and so forth. So that's the geometric progression with a starting element of row and a ratio of row. So we have an arithmetical geometric progression that is defined as the product of an arithmetic progression and the geometric progression. So element by element, so the first element of the arithmetic progression, n minus 1, n minus 2, n minus 3, and so on and so forth, up to 1 for I equals n minus 1, and the elements of the geometric progression, row, row squared, row cubed, all the way up to row to the power of n minus 1, are added together to generate this arithmetical geometric progression. Now, using the properties of arithmetical geometric progressions, we could figure out the sum of it. Because it's finite, it's just n minus 1 elements, so we can plug in the characteristics of both the arithmetic progression and the geometric progression that constitute our arithmetical geometric progression, and say that the formula for the sum of n minus 1 terms is equal to that, and then we just add the first element and get this. So basically, the formula of the sum of the arithmetical geometric progression allows you to express it in terms of just the characteristics of both. So the starting values of both progressions, so the first elements, the difference, the step of the arithmetic progression, which in our case is minus 1, then the ratio of the arithmetic progression, then the ratio of the geometric progression, in our case that's row, and the number of terms we want to figure out the sum for. And using some arithmetic transformations, we could simplify that to arrive at this scaling formula. We can see that that gives us a closed form solution for a time period of n days, given the daily variance, the length of the period, and the autocorrelation coefficient rho. We can see here that if rho is equal to 0, so we have our independency scenario, well then this is equal to 1, this is equal to 1, and this goes away because it's equal to 0. So we'll arrive at daily variance sigma squared times n, just as we would have expected. So it's another easy check that we haven't made any mistakes so far. And as our autocorrelation coefficient explodes to 1, so positive 1, we have a very high degree of positive correlation, then this would tend in limit to n squared. So we will have variance scaling as square and standard deviation scaling linearly. Because if autocorrelation is equal to 1, if the stock return moves to some direction, tomorrow it will continue moving in that direction until the very end of your period, so you can be sure that the standard deviation will be just n times daily standard deviation. But that's a very fringe case that never happens in the real world. It's just a neat mathematical case that we can investigate here. Well, without further ado, we can just apply the formula for the scaling factor here and see if we arrive at the same solution here, and then experiment with various correlation coefficients and time periods to have a better intuition at what this scaling process gives us. So applying this formula, we need first to input 1 plus our correlation coefficient divided by 1 minus the correlation coefficient. That's the first term of the formula that gives us the scaling factor, and then multiply it by this bracket that contains first the number of periods, so n, in our case that's 5, and then we subtract 2 times the autocorrelation coefficient times this ratio that has in the numerator 1 minus the autocorrelation coefficient to the power of the number of periods, so n, or 5 in our case, divided by 1 minus the autocorrelation coefficient. And then we can close a bunch of brackets and force the formula and see that our scaling factor for the variance is 4.82. That is lower than the scaling factor of 5 we would have expected if we assumed independence. And that corresponds to this difference with variance, with scaled variance in case of negative autocorrelation being lower than scaled variance given independency. Well, let's just numerically compare the results. Let's multiply our daily variance by the scaling factor and see if we arrive at the same number. Exactly. So basically, those two methods are exactly equivalent, but you could use this formula to obtain a closed form solution so that you don't have to uh, compile an n by n matrix that can be very time consuming, especially when you try to annualize the variance. Well, now we can just figure out the standard deviations as square roots of respective variances. So here, this is the standard deviation of the variance assuming independence. Here is the standard deviation of the variance assuming autocorrelation. We see it's, again, slightly lower. But what will happen if we either play around with autocorrelation or with the number of periods? Well, first of all, let's say that our autocorrelation increases to 0.99. What would happen? Well, we'll see that our scaling factor for the variance very closely approaches 25, which is 5 squared. So that would mean that our standard deviation will scale linearly, just as we mentioned when we were deriving the formula. Well, and if we change the autocorrelation to minus 0.99, we'll see that our scaling factor for the variance is very close to 1. That basically gives you the intuition that variance scales to a lesser extent the more negative autocorrelation is, accumulating this logic of the negative feedback loop we were previously discussing. And also, unlike in the case of this straightforward approach, given the closed form solution we have derived, you can just change the number of periods and it will give you the result for any input you want to consider. And that's all there is for volatility scaling given autocorrelation. Many thanks for Dingxin Cheng for suggesting this topic for the video. In the comments below, please suggest any further topics in business economics or finance that you would like covered in future videos. And don't forget to subscribe to our channel. Thank you very much and stay tuned.